Have you ever done this kind of optimization? Changing a while into a for, changing if else into switch, changing a function into inline, and then feeling like your code became faster. But the problem is you might have optimized nothing, and in some cases you might have even made your code slower. Today, let's talk about something harsh. Most C++ performance optimizations are actually wrong. A lot of people get stuck on whether for is faster than while. You may have heard all kinds of claims. For is faster, while is lower level, while is more flexible. But the reality is, with compiler optimizations enabled, they are almost identical. Why? Because the C++ code you write does not get executed directly by the CPU. It has to be translated by the compiler into assembly code that the CPU can understand. Let me show you an actual test. When O2 or O3 optimization is turned on, the compiler automatically eliminates the syntactic differences between for and while and translates them into identical assembly instructions. So the CPU doesn't know or care whether you wrote for or while. It only sees the assembly instructions. The core misunderstanding here is you are worrying about syntactic details, but the CPU cares about instruction execution efficiency. Syntax is just for humans. The compiler will smooth out these irrelevant differences. Now, another classic problem, even more deceptive than for versus while, which is faster, switch or if else. Many people will confidently say switch is faster because it uses a jump table, whereas if else uses sequential checks, but that's not necessarily true. The key depends on the distribution of the case values. Let me explain two scenarios. Scenario 1, case values are consecutive. For example, case 1, 2, 4, or case 10 to 20. In this case, the compiler will generate a jump table, which is essentially an array where the index corresponds to the case value, and the value is the address of the code for that case. The CPU simply takes the case value, directly finds the corresponding address in the array, and jumps to execute the code in one step. Time complexity is O1. Here, switch is indeed faster than if else. Scenario 2, case values are sparse. In this case, the compiler won't generate a jump table at all because a jump table requires contiguous memory. If the case values are too far apart, it would waste a lot of memory and become inefficient. So the compiler falls back to the same chain of comparisons as if else, checking from the first case sequentially until a match is found. Time complexity is O(n), just like if else. What's more, if your if else places high frequency cases first, its actual execution speed can even be faster than a switch with sparse cases. So the conclusion is not that switch is faster, but that the compiler decides whether to optimize it into a jump table based on the distribution of the cases. Syntax itself is not the key to performance. Now here's a pitfall even many seasoned programmers step into, thinking inline functions are always faster. It sounds reasonable. Inline is supposed to embed the function's code directly at the call site, eliminating function call overhead. So shouldn't it be faster? But the reality is, inline might not speed things up and could even make your code slower. The core problem is code bloat. For example, you write a 10-line inline function and call it in 100 places. Originally, the function occupied only 10 lines of code memory. But with inline, each of the 100 call sites embeds those 10 lines, turning the total code size into 1,000 lines. That's code bloat. Code bloat brings a fatal issue. The CPU's instruction cache becomes stressed. When the CPU executes code, it loads instructions from memory into the instruction cache. If the code is too bloated for the cache to hold all the instructions, cache misses happen frequently, forcing the CPU to fetch instructions from main memory, which becomes dramatically slower. Moreover, inline is only a suggestion to the compiler, not a command. If the teenline function is too long, the compiler will simply ignore the teenline keyword and treat it as a normal function, because the compiler knows that inlining a long function is counterproductive. So inline is not an optimization. It's an attempt to trade space for time, and it often fails. Only when the function is extremely short and called very frequently can inlining possibly improve performance. Another widely spread claim, the stack is faster than the heap. This statement is not entirely wrong, but it's definitely not rigorous. It's only true under specific circumstances, yet many people treat it as an absolute truth. First, let's look at why people think the stack is fast. Stack allocation and deallocation are automatic, essentially just moving the stack pointer up and down. Allocation moves the pointer down, deallocation moves it up. Almost zero overhead. Heap allocation and deallocation, however, require calling malloc free function or new delete function, maintaining a free list, handling memory alignment, fragmentation, etc. The overhead is indeed larger. But there are several easily overlooked points. First, the stack space is extremely limited. The default stack size is about 1 megabyte on Windows, 8 megabytes on Linux. If you allocate a large object on the stack, say a 10 megabytes array, you'll get a stack overflow and the program will crash. Second, cache and page behavior can be worse. If the stack object is too large, or if multiple stack objects are scattered, cache hit rates can drop. In contrast, heap allocation using a memory pool can ensure contiguous memory and improve cache efficiency. Finally, thread stack implications. In multi-threaded programs, each thread has its own stack. Too large a stack limits the number of threads. The heap, being shared among threads, allows more flexible memory usage, so the stack isn't inherently faster. It's just simpler and lower overhead than the heap for small, short-lived objects that are allocated and frequently. Finally, the most classic pitfall, performance comparison between list and vector. From a pure data structure theory perspective, list is a doubly linked list with O1 time complexity for insertions and deletions. Vector is a dynamic array with ON time complexity for insertions and deletions, especially in the middle. So many people naturally assume list is faster for insertions and deletions, so we should prefer list. But the reality is, in most practical scenarios, vector is much faster than list for insertions and deletions. Why is there such a gap between theory and practice? The core reason is cache hit rate, which is the most overlooked yet critical point in C++ performance optimization. Vector stores elements in contiguous memory. When the CPU loads one element of a vector, it also loads nearby elements into the cache, spatial locality. Subsequent accesses to nearby elements are served directly from the cache, extremely fast. List, however, is a linked structure. Each node may be located in a different area of memory. After the CPU accesses one node, the next node is likely not in the cache, causing frequent cache misses and forcing the CPU to read from main memory. The overhead of pointer chasing plus cache misses far outweighs the ON cost of moving elements in a vector. Moreover, vector has another advantage: lower memory overhead. Each node in a list needs to store 2 pointers in addition to the data, significantly increasing memory usage. A vector stores only the data, achieving higher memory efficiency. So theoretical complexity winning doesn't mean actual performance wins. So why do people keep happily performing these ineffective optimizations? Because these optimizations are visible. You can directly modify the syntax, see the code change, and feel a sense of achievement. I'm optimizing. But what truly determines C++ performance are the invisible things. If you really want to understand C++ performance, know why code is fast or slow, and escape the trap of blind optimization, you can subscribe to this channel. Alright, that's it for today. Remember to like and subscribe. See you next time.